In Year 12 Chemistry, you're going to learn that we've been lying to you about chemical reactions. What we've always told you is that chemical changes are irreversible, which means if you have your reactants, they react, they make your products, and that's it. But that's a lie, because in Year 12 you learn that reactions are actually reversible. What that means is this little arrow here, which only goes one way, should actually look a bit more like this, where the reaction goes both forwards and backwards. How does this actually work? Well, it's in a process called equilibrium. Equilibrium is the point in a reaction where you have products and reactants in a system, but their concentrations are no longer changing. This generally happens in closed systems. To work out how this happens, let's look at it in terms of collision theory. The graph below talks about the rates of chemical reactions over the process of a reaction that's coming towards equilibrium. Let's first of all look at the start of our reaction, which is way over here. What we've got here is a whole bunch of reactants and no products. What does this mean in terms of collision theory? We have a high concentration of reactants, so therefore we have a high amount or high frequency of collisions between these reactant particles. That means our rate of our Ford's reaction is very, very large. On the flip side of that, at this point in time, we don't have any products formed. That means that the backwards reaction cannot occur at all. Immediately after we start our reaction, these reactants start to react and they start to go away. What this means is that after our initial large amount of reactants, this concentrations start to decrease because they turn into products. What that means is that the frequency of collisions between our reactants starts to decrease, and then our frequency of collisions between our products starts to increase. So therefore our rate of reaction for our Ford's reaction starts to go down, and the rate of our backwards reaction starts to increase because we start to produce our products. Eventually, you'll get to a point where the rate of our Ford's reaction and our rate of our reverse reaction are actually equal, and the frequency of successful collisions between our reactants banging together to make products and our frequency of successful collisions between our products banging together to go backwards to reactants, that is at an equal rate. So therefore, we have reached equilibrium, where the concentration of our reactants stays the same because the number of reactants producing products is counted by the number of products producing reactants, and that is where equilibrium is made.